Back in intro physics, we looked at the principle of interference between multiple wave sources at a very basic level. Given two fields that can be modeled as sines or cosines, either as functions of position, time, or both, we said that we can find the net field at some location by adding the one to the other. If the two sources are in phase, they add up peak to peak, trough to trough, and we get a much stronger wave. We called this constructive interference. And if we had two sources that were exactly out of phase, they add up peak to trough, trough to peak, and cancel out entirely, which we called destructive interference. And then we latched on to a general principle. Given two sources of the same wavelength, starting out in phase, the same polarization, good coherence properties, and the same intensities, whether or not we got totally constructive or destructive interference was reduced to simply looking at the distances that light from each source had to travel to some target, and then taking the path length difference. If that path length difference were any integer multiple of the wavelength, the two sources would arrive at the target in phase, and we'd get constructive interference. And if it were any integer plus a half multiple of the wavelength, the two sources would arrive totally out of phase, and we'd get destructive interference. This is obviously a fairly limited picture of interference. That bulleted list of restrictions was pretty long, but it was appropriate at the time. Now, however, we know how to treat electromagnetic fields in detail, and can do interference and all the related phenomena more completely. In general, figuring out how two fields interfere will always be as simple as taking the one field plus the other field. Usually we'll be interested in intensities, so some kind of EB star gambit to get at a time average will be appropriate. Let's start with two plane waves of the same frequency, polarization, and amplitude, arriving at some location such that one is out of phase with the other by some angle delta. The net field is easy enough, and we'll get the time averaged intensity through the Poynting vector, using B star instead of just B, and an extra factor of a half. We crank this on out. Most of the terms drop out, and what remains can be grouped rather suggestively. Recall that e to the I something plus e to the minus I something over 2 is cos something. Note that I'm defining I0 to be the time averaged intensity of any single wave. So 1/2 E0 squared over mu naught c. So here's our final expression for the intensity of the combination. And a sketch of intensity versus relative phase angle. And it's consistent with our expectations. There's a baseline of twice the intensity of each source individually, modulated by a 1 plus cos delta term. When the delta equals 0, the waves are totally in phase and we get 4 times the original intensity. And when delta is pi, the waves are totally out of phase and we get 0. This approach doesn't really have any restrictions to speak of. Were the sources of different intensities or wavelengths, we'd still do basically the same thing. By hook or by crook, find the individual fields at some location, sum them, and then find the time averaged total intensity. At this point, you might reasonably ask what we should do differently if the fields don't have the same polarization. And the answer is not a whole lot. If the fields need to be explicitly treated as vectors, no problem, do that. Let's have two plane waves out of phase with one another by some angle delta, and with their polarizations offset by some angle theta. To keep it clean, we'll give them the same amplitudes and frequencies. Note that I'm letting up on the picture be the j-hat direction, and that I'm writing the j-hat term first. Now, before we do math, it's reasonable to have expectations. Given the vector nature of fields, I might expect that the component of E2 that's parallel to E1 will be responsible for the interference, while the component of E2 that's perpendicular to E1 will just kind of be along for the ride. And that is indeed what happens, though I don't consider it super obvious what exactly that would look like. So let's work through the details. The net E field is easy enough, but the real money's in the intensity, so let's get that too. We can get the time-averaged Poynting vector by taking E cross B star with that factor of a half. So if you wanted to be thorough, you'd write down the complete B fields corresponding to E1 and E2, sum them, and then do your cross product. But I'm lazy and I can't help but notice that for plane waves, E and B are perpendicular and have magnitudes related by a factor of C. So the magnitude of E cross B star is going to be the same as the magnitude of E dotted with E star over C. The cross product of two perpendicular vectors gives you a result that's the same magnitude as the dot product of two similarly sized vectors that are parallel. That'll make the next steps pretty easy, as long as we're real careful with signs and such. Group our trig factors and our complex exponentials. Move some 2's around. And there you have it. Remember, delta is the phase angle and theta is the relative polarization angle. When theta equals 0, the two sources are of the same polarization and we get, which reproduces what we had before. When theta equals pi over 2, so that the two sources are of orthogonal polarization, we get, and that doesn't depend on phase angle. So that's what it means for perpendicularly polarized sources to not be interfering with one another. Interference is pretty much by definition a dependence of the result on the relative phase angle. So that about does it. If you want to generalize further and have dissimilar amplitudes or even different frequencies, you still do the same procedure. The only other thing we haven't talked about that can impact the result is the notion of coherence. And that's a big enough topic that we'll need to handle it all on its own.